Okay, so just briefly reminding ourselves what we talked about in the last class, since the written part is not available with me. We talked in general about Coulomb's law, the simplification that Gauss law provides. And from there, we sort of went into the curl of the electric field, which is zero. We talked about it being conservative. And then we went into the discussion on the line integral, the closed line integral of the field. And we talked about the meaning of this. And after doing everything else, we ended up with a new quantity, which is the potential. And we talked about it from the point of view of work done. We also discussed about its relationship with potential energy. But it comes down to basically calculating this line integral, where we also, I talked in detail about this reference point and what it means. So that would be something that that is important. And then how you can calculate the potential given a field, and also given potential, how do you calculate the electric field? So this was the main point of discussion in the last class. I did talk about the simplification that the potential brings in for certain classes of problems, typically the ones where one cannot apply or use Gauss law in order to obtain the electric field. And I took up a specific example of the electric dipole. I think electric dipole in one of the tutorials also it will come. But anyway, I did it in the class so that you get a feel for how the potential, it simplifies certain kinds of calculation. So a few more comments I would like to make on the potential part. This is our 15th class. This is October. So a couple of quick comments that I would like to make. So potential, so let's try to understand the potential in a geometric way. So if we have a point charge and we are calculating the potential due to that. So for a point charge, the potential would be simply given by or R, whichever way you want to write. And realize that given the values of the charge and the other constants, you can rewrite this expression as x square plus y square plus z square being proportional to, we know what that function is, but I'm just writing the inverse of the potential. And we know what kind of surfaces this expression represents. So if I were to simply sketch it for a point charge for different combinations of x, y, and z, such that the value of the potential remains constant on them, we will have these surfaces. It's spherical, but I'm drawing it on a plane. That's why it's circular. And the property that it will have is that for each of these circles that I have drawn over here, the potential remains the same. So let's say V is equal to some 100 volt over here, some 50 volt over here, and so on and so forth. These surfaces, so first thing to realize is that the potential takes a particular value, and this is why we are able to give the value of a potential, right? The potential is this much. So it taking a specific value over a surface, Okay, and provided there are other things, but just focus on this part right now. Allows us to give a value to the potential, and these surfaces are what we call equipotential surface. Now the field, we know these are things that I have talked about when we were discussing gradients also. So field is related to the potential, right? It's the negative gradient of the potential. So any point on this equipotential surface, if I were to calculate the electric field, since the relationship is in terms of the gradient, it will be pointing outwards. And these are the field lines that we are used to drawing. So in this sense, we can have a visual description for both the potential and the fields. And if you recall in the last class, the example of dipole that we did, I asked this question about whether you can use Gauss law to calculate the electric field directly for the dipole. And the difficulty over there would be in choosing the appropriate Gaussian surface. And you can appreciate it by again thinking in terms of this equipotential surface. I'm not going to write the expression again for the potential, but what we can say certainly is that, let's say I have a positive charge plus Q over here, and I have a negative charge minus Q. And let's assume that the charges are very far away. This is not really the dipole picture, because in dipole we had them to be very close to each other. But let's say that they are very far away. So under that assumption, the equipotential surface would be the exact same as we have drawn in the previous page for a single point charge. However, as we try to bring these charges closer to each other, then these equipotential surfaces will get deformed. So let's say I try to bring them close to each other. So what will happen is that the equipotential surface will be modified, and it would not be, or it would not have that nice spherical shape that we had for a single charge. The electric field still obeys the same kind of relationship with the potential. But now when you draw the or sketch the electric field lines, it would, for instance, so let me draw a few more circles. So close to the charge, you can still assume that these are almost spherical. But as the distance increases, because there are these two charges and you have this whole superposition thing going on, there will be some overlap. And the field lines over here, it is like a single charge, but it's going to change. And this should give you a feel for why the Gauss law would not be a good method to use when it comes to calculating the electric field of a dipole. So this is a side point that I wanted to just mention, so that first of all, you are aware of what you mean by equipotential surfaces. And secondly, when you think in terms of electric field lines and directly trying to apply Gauss law, what kind of complications can come. So this was the main thing that last class, since I didn't have time, I could not point this out to you. So these are essentially some of the things that I have covered when it comes to electrostatic potential. I just now talked about equipotential surface, and these are surfaces on which potential has a constant value. And the property of the electric field is that it is perpendicular to these surfaces, and that it being perpendicular is also reflected in the kind of relationship that the electric field has with the potential itself. we have defined what we mean by potential. The potential between points A and B is the work required for per unit charge to carry a particle from A to B, and work per unit charge. So I think that is something that I would highlight also. And that is why potential is not potential energy. The other thing that we have been talking about is the potential itself being scalar. It's an easier quantity to calculate, but at the same time, the electric field, which is vector, and potential, once you have calculated the potential, you can get to the electric field, is a vector. And calculating a single scalar quantity, it allowing you to get an estimate of the electric field in all possible directions. It's quite remarkable if you think about it. And the reason that it becomes possible is essentially because of this relationship that we have, which is the curl of the electric field is 0, which basically relates the field in different directions. So it's not that they are independent of each other, they are dependent on each other. And that is why calculating a scalar quantity, it allows us to evaluate a vector quantity over here. The other things I don't need to go through them again. So reference points I've already talked about, principle of superposition, why principle of superposition applies as you go from force. Remember, force was an observation, right? It was a fact, in fact, that we were using. From force, we found out that the electric field itself is obeys superposition, right? And the reason that mathematically, if you are more mathematically inclined and you want to think about why this is so, so also remember that there is a very simple scaling relationship that is there. So you take the force and you scale it with the charge and you get the field. That's why the superposition applies there. You take the field and then you again have a linear operation for the potential, and that is why the superposition is also obeyed by the potential itself. And the final thing, which you by now you know that in the exam it matters, is writing the right units in the SI system. So these things you can make a note of. I don't have much to add over here. But let me try to now take up an example and point out a few more things for you. And this, I think this is a solved example also, but the thing that I would like to point out, maybe it's not a part of that solved example in the book. So as an example, let us consider a spherical shell SH with charge Q and a radius R. And let's say we want to calculate the electric field for this. And this is a very straightforward example when it comes to application of Gauss law. So it's in fact, you can calculate it in one step itself. So we know that for the spherical shell, there is no charge that is within the shell, and hence inside the shell, the electric field is going to be 0. All the charge is on the surface, and I've given the net charge. So outside also, it's trivial to calculate the electric field. So the electric field inside, and by inside what I mean is for values of small r, which is less than the radius of the sphere, it would be equal to 0. And outside, which is r larger than r, it would be equal to 1 over 4 pi epsilon naught q over r square. And this is straightforward. So that's why I'm not drawing anything and not trying to say much on it, because these are trivial examples given what we have already covered. From the field, I can obtain the potential also. Let me first calculate the potential outside. Okay, And this would be given by some reference point to R. Again, I'm assuming that all these dot products in the integral and all these things are fairly clear. So I'm not writing all those steps. So it's going to be Q over 4 pi 1 over R square dr, which is simply, I could have written it directly also. What about the potential inside? So realize that this integral that we are conducting, the electric field will be non-zero till the surface. So from outside till the surface, and within it, it's going to be zero. So the entire integral from a reference point to this value R, which is inside the spherical shell, you can split it into two. One is till the surface and other is from the surface to a point inside the shell. The second integral, which is from the surface to a point inside the shell, since the electric field is zero, that will not contribute at all. And then what you will have is the potential would be given by where R is the radius of the sphere. Let's also sketch each one of them. These are things that we have done earlier. So if I were to make a sketch of the electric field with distance, till the surface there is nothing, and then it takes some value over here, we know what that is, and it's going to fall down as 1 over R square. For the potential, if I were to make a similar sketch, within the sphere, the potential is a constant because all the quantities on the right hand side, they are constants. So it's a constant till the radius of the sphere. And beyond this, it falls down as 1 over R. And the point that I would like to bring to your attention is the following. So if you were to look at the behavior of the electric field itself, what you will observe, and this is typical of many of the problems that we have been looking at till now, is there exists a discontinuity at the surface for the electric field. However, for the potential itself, it is continuous. There is no discontinuity that exists over there. And even if you are just focused on the field right now, what is clear is that all the action, it essentially happens over here. On either side of the boundary, the behavior is quite regular. It's just very close to the boundary that you observe something weird happening, like this discontinuous jump that is over there. So you can say that the general behavior of the electric field, it is quite simple, except at the boundary. So in fact, I am going to write it down. So except at the boundary, the rest of the behavior of E is quite simple. So if I could figure out a way to connect the behavior of the electric field from a point which is to the left of this boundary to a point which is just to the right of this boundary, then the remaining is quite straightforward because there's not much over there. So let us try to figure out a way in which we can relate the values of the electric field on either side of the boundary. And we're just thinking of points which are just to the left in the way that we have drawn, and the point to the left. So just below the surface and just above the surface. So let's say that we have some arbitrary surface like this. And the treatment is quite general. Okay. So let's say that the electric field on one side of the surface we write as E1, and the electric field on the other side of the surface we write as E2. Now these are vector quantities, so I can decompose them into normal and tangential components. So let's say that I can decompose it into a normal and a tangential component. Normal means normal to the surface, and tangential means tangential to the surface itself. And the job is the following. I would like to relate the normal component of the field on either side and also the tangential component of the field on either side. And we'll also assume that the surface carries some charge density, which we can write as sigma. So for the normal component, we'll do the following. So again, I'll draw my surface a little bigger than the previous one. I want to do the tangential and normal both on this same thing. So I know that if I were to draw a small pillbox such that, so I'll make it big, but remember these are just adjacent points on either side. So if I were to draw a small pillbox of area A, this area, we'll call it to be A, I can use Gauss law to relate the normal component. So it's a very small pillbox. So the normal component of the area element, it points in a direction, which is since it's very small, I'm assuming it to be very small. So the electric field will also, the component along this direction is the one that matters. So that's what we are essentially doing. So using Gauss law, we have a normal component E2n over here and a normal component E1n in the other direction, the way we have drawn it. So it's the electric field times the area, right? The normal component of the electric field times the area that we are looking at. So it would be E A. And then for the electric field on side 1, the normal to the area and the electric field, they're pointing in opposite directions in the way that we have drawn it. So I can write E1 normal. And this would be equal to the charge that is enclosed which is sigma times the area divided by. So I can write now minus a. So I hope you realize that this is quite general, and the outcome of this is that if you look at the normal component of, if you try to relate the normal component of the electric field on either side, there exists a discontinuity, and that discontinuity is given by the term on the right hand side, which is the charge density divided by the permittivity. So the normal component is discontinuous. Let's now talk about the tangential component, and I'm going to draw it over here. So tangential component. For the tangential component, I need to think about the component that is tangent to the interface or the surface. And the vector relationship for electric field, which allows me to do that, is the line integral itself. I can, for instance, draw a small rectangle like this, such that it covers both sides of the interface. And I can then look at this closed loop line integral E dot dl. Let's say that this length is L. And this other dimension, it doesn't matter, because the way we are thinking about it, you can put it, it's not a big deal. The result doesn't change because of that. But we are considering it to be very small. In fact, we are just coming very close to the surface itself. So let's say that I take this path to compute the line integral. So this would be equal to, okay, and these are things that we have done. That's why I'm not writing a lot of things over here. The assumption is that it's more or less clear to everybody. So it will be the tangential component of 1. So this is the first side. So let me call it 1 over here. I said the second and fourth, they will not matter, because we are going in opposite directions. So anyway, they will cancel each other out. But just think of them to be, that dimension to be very, very small. That's all. So this times the length. For the side 3, it would be minus e to t. So it's the tangential component is in this direction. The line element is in the opposite direction, L. And we know, given the relationships, that the closed loop line integral, that should be 0. And which gives us that the tangential component of the electric field, they are the same on either sides. So what we have is that we have related the components of the electric field itself on either side of the interface. What I have done over here is what would fall under what you call boundary conditions. And our objective being to figure out different ways in which we can calculate the electric field in simple ways. This provides us with another tool that can be used, and it has more applications than just being something that you can do like this. So when you come to the electrodynamics part, I don't think that the course will in fact be able to go over too much into the details of this, especially when it comes to optics. By relating the normal and the tangential components, you can in fact derive all the laws, Snell's law, conditions for total internal reflection, by simply looking at the relating the electric field on two sides of the interface, right? There also you have an interface, light comes, bends towards the normal, away from the normal. This is what Snell's law would give you. So all those things, they are fallout of what I have just presented. So this is going to be the tangential component is continuous. How does this relate to what the example that we have just done? Okay. So if you think about the shell example, inside, let me go back to the spherical shell example. We know that within the shell, the electric field is 0. So both the normal and the tangential component of the electric field, it is going to be 0. On the other side, which is outside, just outside you're thinking of, the tangential component is also going to be 0 because the tangential component is the same on either side. As far as the normal component goes, this would be equal to sigma over epsilon naught, which I can write as charge divided by area, which is 4 pi r square. So I hope you see that if you make such kind of observations, then you can simply look at the boundaries, what goes on at the boundary, and you can try to relate the electric field on either side. And there are places where we will use it, but since we are already following this thought, I thought that we should at least talk about these things. Also, I've shown this already, that the potential on either side is the same. So V1 equal to V2. So this is continuous. And given that the normal component, it experiences a discontinuity, so the gradient of the potential is discontinuous. In many instances, you have information only about one side, and by using such relationships, okay, you can obtain the relevant the value of the relevant parameter on the other side. You have just what we have done here is we have obtained the value just close to the surface. We know that from here we can extend it to any place by simply replacing this r square by that distance. That's all that you're going to do. Okay, so I'm going to write. So don't think that it's a constant, but rather it depends on the distance outside the spherical shell. Okay, so I hope that these things are clear. These are tools that you can use. And maybe one more relationship we can talk about before we get into the next topic. So what we have done till now is we have talked about Gauss, we have identified a relation between the field and potential. If we put both of these together, so for the electric field, I'm going to use negative gradient of the potential. So this would be equal to the Laplacian of the potential with a negative sign. And there is some disturbance. Okay, if you have a question, then you can unmute and ask, or wait till the end of the class. All right. So what we have is then that the Laplacian of the potential is given by the negative of the charge density divided by the permittivity. If it is a charge free, so this expression is what you call the Poisson equation. And if rho is, if it's charge free, if the region is charge free, so if rho is equal to 0, then you have the right hand side as 0, and this is called the Laplace equation. If you're thinking why one needs all these different tools, the answer remains the same as earlier, because given a problem, you're trying to figure out ways in which you can calculate the potential, the field, or the charge density itself. Now, if you're thinking where this will come in handy, the Poisson and the Laplace equation, I will do it in detail. There will be a tutorial also on this. But just to give you an idea, so imagine the following situation. So let's take an example. Of a parallel plate capacitor where the distance between the plate is d. And let's say that there is some charge on the top plate and it's kept at a potential some V0, and the bottom one is grounded. And let's also assume that it has infinite extent in xy, and this direction is the z direction. So the only place where the charge appears, and see, I've talked about equipotential surface. That's where I talked about it having a value. So the potential has a specific value on either plates, but there are no charges within the plates itself. So now, if I want to calculate how the potential itself, it varies between the two plates. So since there is only a single dimension that is of in which the potential is going to vary, there is no variation in the x and y. So I can, within this region, I can solve the Laplace equation. Okay, so this is within the plates. And for our specific case, it would be only the z direction that matters. I'll do a few more examples, but I just want you to get an idea of how you work through these things. Now, I can solve for V immediately. This is a very straightforward second order equation that, to solve. So you integrate it once, you'll get a constant. You integrate it one more time, you get a constant times z plus another constant. A and B are the constants of integration. And this solution is valid within the plates itself. However, to get to the unique solution, and this is true every time you solve these partial differential equations, what you do need is the value of the potential at the boundary itself, which is known to us. So I know that for z is equal to 0, okay, so this is z is equal to 0, and this is z is equal to d. The potential is equal to 0. I input this, and this will give me the constant b takes a value of 0. I know that at the top plate, Z is equal to D, the potential is a constant, which is V naught. So what I will have is V naught equals A times D, which gives me, for the constant A, V naught over D. Putting all these together, the potential, the unique solution is over D times Z. What have I learned? What I have learned is that if I were to draw the potential with respect to Z, and let's say this is D, so it's only till here. So it takes a value 0 at Z is equal to 0, and it takes a value V0 at Z is equal to D. And from this point, the lower plate to the upper plate, it varies linearly, and the slope of this is in fact the constant that you have before the Z, V naught over D. Once you have determined what this potential is, getting to the electric field is straightforward, because all that you will do in order to get to the electric field, you'll take a negative gradient of the potential with respect to Z. You'll get a V naught over D, the Z direction. So even though this looks like a very trivial and straightforward example, you could have in fact said that if I have two parallel plate capacitor and the charge is given to me, I can easily calculate the electric field. But remember that in most situations in these capacitors, it's the potential marking that is given to you, not the charge density. Given that potential value, knowing well that the value essentially gives you information about this equipotential surface. So on that particular surface, the value remains constant. You can get an estimate, or you can get an expression, you can solve for the potential as well as the field. And this applies even if the region within the two plates, it had charges in it. Even if there was some kind of charge density that existed, we put some charges within it, we introduce a material which has this charge, we put a conductor inside it, for instance, it's the right hand side that is going to change. That's the only change that is going to come. I'll talk in detail about all these things and some other methods that comes out of this, but at this point, realize that what we have achieved till now, what we have achieved, I hope these things are clear. If not, you can always ask me, is that when it comes to electrostatics, you have the charge density. This is a figure straight out of Griffiths. So you can also refer to that on this one. And so it's basically three fundamental quantities that we have looked at. These are the charge density, the electric field, and the potential itself. We started by talking about ways in which, given the charge density, we can solve for the field. Writing dq just because I think that's more general, because any charge distribution you can handle from there. Then we go into Gauss, which basically, given field also, you can calculate the charge density, or given charge density, you can calculate the field itself. From electric field, you can calculate, let me put the arrow like this. From given electric field, you can calculate the potential by taking the conducting this line integral, okay, from some reference point to the point R. And given the potential, you can calculate the electric field via the negative gradient of the potential itself. Given the charge density, we know how to calculate the potential. This is and given the potential or even otherwise. So these arrows, they are bidirectional in fact. So this, we can use the Poisson equation to calculate the potential as a derivative, or you can calculate the charge density itself. And we began by having just two experimental observations. These two experimental observations were, one was the superposition itself, which we didn't really, there's no means in which we can prove it, but we say that this is an observation which seems to hold true. It's a strong statement in itself. Not always this is going to be valid for, but for a large class of problems, such as the ones that we are dealing with in electromagnetic theory, superposition works quite wonderfully. And the second was the fundamental law of electrostatics, which is the Coulomb law. And now what we have in front of us is a complete description or a set of mathematical tools, complete set I would say, to calculate one or the other quantity. And having calculated one, you can calculate all the remaining two by using these different formalisms. So what we have essentially talked about is, given if you have symmetry, for instance, use Gauss law. If there is no symmetry, maybe potential is a good starting point to have. I gave the example of parallel plate capacitor, and you can construct a lot of these examples in different coordinate system. If time permits, I will take a few of them in the class itself. Not today though. But this is all. So this gives you a complete picture of all the different discussions that we had till now. Okay, so I hope that till this point things are clear. If not, you can always ask me. The boundary conditions will discuss about it a bit more as we go along. Okay. So these are things that we have discussed till now. So let's move forward. So till this point, I hope everything is clear. Now let me go back to one of the discussions that we had, and this was regarding work done, which I talked about in detail in the last class. I also tried to connect it with the with some aspects in mechanics. And work done, given the definition of work, is the following integral. And the way we thought about it was, what is the energy that one has to expend in order to move against or do work against some applied field? So this was the way that we thought about it. And from here, we started from here, and what we essentially did was we came to the potential representation. So work done, we wrote as, for electrostatics, A to integral E dot dl Q times A minus VA. And from here, we obtain that the potential difference between 2 points, that is the work done charge. let's say we are interested in, again, these are things which will slowly, as you see the applications, it will become clear. But let's say that we are interested in calculating the energy that is inside a charge distribution. You can think about this question in the following way, that let's say that you have a collection of charges. How much potential energy do this collection of charges they represent? And in order to answer that question, we can again go back to mechanics and we can try to see what we mean by that. So maybe it will become more clear if I take up an example from mechanics, and we go back to one of our simplest and favorite examples, that you have this incline. You have a mass over here. Let's say that this height is h. And if I asked you the question, what is the energy stored in this ball that we have drawn over here? So this is a ball. And we ask the question, what is the energy that is stored in this ball? And this energy, we know what it is going to be. It's quite straightforward. It is mass times gravity times this height h, right? That's the potential energy. You can think of it in another way also. So if I were to just release this ball, it is going to fall down. As it falls down, it is going to release kinetic energy, and that it is going to have kinetic energy. And eventually that energy is the same as, when it comes down, as this potential energy that is stored in the ball itself. So if we are thinking about this question, or you're trying to answer this question about how much energy is stored in something, the alternate way to think about it could be, what is the energy that is required in order to, so we are thinking about energy that is going to be released, but in another way of thinking, you can also think in the following way, that how much energy is required to put it over there. So in this case, to put the ball at a height h, the energy that is stored is mgh. So the amount that is needed in order to put it over there, that's going to be mass times gravity times the height. So if we are really interested in calculating the energy that is stored inside a charge distribution, and let's say we are thinking in terms of n discrete charges, we can answer it by calculating the amount of work done to assemble So I hope that this argument is clear. What we are interested in calculating is the energy that is stored inside a charge distribution. And the way we are thinking about the problem in itself is that this energy that is stored should be the same as the energy or the amount of work done that to assemble all these charges together. And it comes straight out of the analogy that we have drawn with the mechanics problem of a ball at a height. And this is a problem that I know very well how to calculate, because this is something that we started with when we talked about and we got to the potential part, right? Because if you recall, the way we had done it was, we have some charge q because due to which there is some field, and then we asked the question, how much work it's done to take a charge capital Q from point A to point B. given that there is an electric field that is in that region because of this test charge plus Q. And that was our basic idea, or the thing that we used was our basic work done arguments that we had used. We'll use the same idea in order to calculate the work done to assemble all these charges. So let's say that there is nothing to begin with. And what I do is I take a charge, I'll call it Q1, from very far away, and I bring it to a location which I mark as R1 in this coordinate system. And this is charge Q1. And somewhere over here is infinity. So if I were to calculate the work done to bring the charge Q1 from infinity to this location R1, let's call it some W sub 1. This has to be 0 because there is nothing else over there. This is not like the previous problem where there was a charge over there due to which the field was there. So there's no field acting, so there's no work there. So it does not have to do any work against the field that is over there. So this for it is simply going to be 0. Now let's say that we have put this charge Q1 over here, and now from infinity I bring another charge and put it at a location Q2. At a location R2, this charge is Q2. So work done to bring Q2 to R2. This would be equal to, so W, I'll write it as W2. It would be equal to the charge itself. Okay. This is something that I wrote in the previous page also. It's Q times the potential, and the potential, it was the potential difference, but the one point is very far away, so the potential is going to be 0 times the potential from Q1 at the location R2. Okay, this is the destination point, which I can simply open up and write as 1 over 4 pi epsilon naught Q1 Q2 divided by R1. I'll write it in shorthand notation where Rij, this is equal to J minus Ri, this distance. Okay, so I know what would be the work done to bring the charge Q2 to a location R2. We'll do one more, and I think that will make things very clear. So let's say I take another charge and bring it to, so the charge is Q3, and I bring it to a location R3 now. So one by one we are assembling it. So for this charge Q3, if I calculate the work done to bring Q3 to R3, so this would be, let's call it W3. This would be the charge, which is Q3. And now the potential that will be present, it will be the potential from both charges Q1 and Q2 at the location R3, right? And we know that the potential superposition is valid, so they are just going to add. So this would be equal to 1 over 4 pi epsilon naught Q1 Q3 R13 plus Q2 Q3 over R23. And now everything is clear. It's right in front of us. So I can now simply
use induction and move forward from here. It's as simple as that. So for any arbitrary charge Qi, let's call it the work done to bring that charge Qi as W sub I can write the work done to be Qi divided by 4 pi epsilon naught. The sum over all the other charges that are there. And this goes from, the summation over j goes from j is equal to 1 to I minus 1 divided by j. This is this r that I am writing, Rij. And with this, I can now calculate the total work done, because now I have the work done to assemble each one of these charges sequentially. And all that I need to do is sum over all these different work dones in order to calculate the total work done. So total work done let's call it W. This would be equal to sum over I Wi. We have already obtained an expression for this, so I can write it to be sum over I Qi divided by 4 pi epsilon naught sum over sum over j such that j is less than I. This is how we had written. J goes from 0 to 1 to I minus 1, and then Qj over Rh. What I can also do is, and if this is not clear, just let me know and I'll explain it in detail, but I can sum over all the j's, okay, not just j less than I. And then to account for that overcounting, the twice counting, I can put a factor of 2. And this entire thing now I can write as sum over I Qi. I'm just writing it in a form such that I can point out the main part to you. Sum over j Qj divided by Ri. Okay. The reason I have put this 2 in the denominator is if you just go and look at the expression, for instance, for W3, we have Q1, Q3, Q2, Q3. These are the two terms. So I could have, for instance, for this written, it's Q3 times the summation is basically Q over 1 and 2, the indices 1 and 2. I can in fact not limit it to only these two. I could have other terms also, which could be Q3, Q1, not Q1, Q3. So I'm just changing the product, and Q3, Q2, but other things remains the same. So I'm just putting a factor of 2 in the denominator. So it's not just j goes from 1 to a value which is less than I. J takes all the possible values, where the possible values are essentially the total number of charges. And then you're putting a factor of 2 in the denominator. So that's the only maybe not so clear thing that I would have done. But realize that this part over here, we already know what that is. This is by definition the potential at the location I due to all the other charges that are going to be there. So I'm going to write it as VRI. And now I can simplify and write for total work done. This is equal to, and that is the, in fact, the final part when it comes to discrete charges. This is half times sum over I Qi times V.
the work done to assemble a charge distribution. And that is the same as the energy that is stored in a charge distribution. This term, potential term that we have, this is the self potential of the distribution. So it's basically all the other charges and what is the potential. And this simplifies this calculation because given a collection of charges, so you're not really going to bring each one of them and keep on adding it. If you bring in a new one, all that you need to know is what is the potential due to this existing charge distribution at this location, and you are done. So calculate the potential and you. So we'll take up some examples again in the tutorial, I think. But if we are interested in calculating the energy that is stored in a charge distribution, and I think that's the conceptually that's the main part, that you can think about it in terms of the work that is done in order to assemble this charge distribution, and that is the same as the potential energy that is contained in the charge distribution. And from there, you can obtain, or rather we have obtained an expression for the discrete case for this charge distribution, for the work done. Let me also take it a little bit forward. And let's say we had a continuous distribution of charges. So for the discrete, what we have just obtained is it's half sum over I Qi VRI. And at this point, what we will simply do, we will not try to think a lot. We'll simply take it to continuum by changing the summation to an integral. We'll put a half, which is this half over here. And then it's the standard thing that we do. It's the charge density times the potential. It's a volume integral. There are a few things that I'll point out later when you do, as we do this direct conversion. There are a few sticky points over here, but they will not really be important for, again, for the kind of discussions that we are having right now. I'm almost out of time, but I'll still, let me try to put it in a form. If it is not clear, then we'll take it up again in the next class. So what I can do at this point, just to write it in a more simpler way, I can write for the charge density by using Gauss law. In the following form. So for this work done, I'll have, so I'll bring this outside the integral. Chance of the field. Now, potential is a scalar and the electric field is a vector. So what we can use one of the vector identities, and there's not much to say over here. It's just trying to get it in a form which is very handy. So that's all that we are doing at this moment. We are just changing the form. We could have stopped at this point when we wrote it in the integral form, but we are just putting it in a different form. So that's all that we are doing. So if you recall, if you have a divergence of a scalar times a vector, this we can write as the scalar times the divergence of the vector. These are vector identities that we had done in the initial part, plus
the dot product of the vector with the gradient of the scalar. And what is inside the integral is the first term over here. So I can change this. This is a volume integral. So I can rewrite this integral as the divergence of the term on the left minus the second term on the right. I'm taking it to the left. Also realize at this point that I can use the relationship, which is the field is the negative gradient of the potential. So negative, which is outside, gradient of the potential. So the second term I can write as okay, I'm out of time, so I'll just show you the final result. I'm going to argue why that is correct in the next class. I don't want to take too much of your time. So the first term, which is the divergence integral, I can convert it into a surface integral and write it as. So I'm using almost everything that we have discussed till now. So I'm using relationships between these different quantities. I'm going into divergence theorem and everything together. What I will show in the next class, I'll give you the answer, but what I will show is that this entire thing that we have over here can be written as simply the first integral. I'll argue it's a surface integral which will go to 0. It would be given by only the second part, which is volume integral. Okay, for continuous charge distribution, given the electric field, if you want to find out this energy that is stored within that, you can simply conduct the integral that we have. These final things I will talk about it in the next class. That would be my starting point. The steps in the derivation I have done. Why you can set this first term to be equal to 0. So why I can do that. I will talk about it in detail. That takes around 5 minutes or so, but we have already exceeded our time. So let me stop at this point and I'll continue with this discussion in the next class. If you have any questions, you can always ask.